Hey everyone, welcome back. It's been quite a while, hasn't it? I'm back and I'm really excited today to talk to you about coding recurrent neural networks, or RNNs. Now this is going to be a follow-up or an extension video to our theory behind RNNs video, which is linked at the top of this notebook and also in the description of this video. It'll be super helpful to have watched that before, so you can map all of the theory you know to the code you're about to learn. So we're going to structure this pretty simply. We'll be looking at a series of tasks which we'll hope to solve using RNNs. The tasks will get increasingly complex, but they'll all share a common theme, which is the theme that RNNs are built to address: sequence modeling. Given some sequence of numbers or words, how can I use a recurrent neural network to best predict what's going to come next? So starting here, we'll look at the imports. Usually we don't dwell too much on the imports in these videos, but we're importing new things here that we've never imported in previous videos, and for that reason I think it's worth a little bit of an explainer here. The first thing we're importing here that's worth mentioning is TensorFlow. Now chances are, even if you've never used this before, you've probably heard of it. It's very ubiquitous nowadays. I think it's worth a quick one-line explainer on what it's all about, and you can definitely research more on your own. TensorFlow, in a quick one-liner, is a library specializing in helping you code neural networks. Again, tons more to be said here, but that's the TLDR. The other library we're going to import, and the one we'll use a lot more in this video, is called Keras. I had a lot of confusion about what's the difference between TensorFlow and Keras. Are they two different things or the same thing? Hopefully these 3 lines in these comments help demystify it a little bit. So Keras is a Python interface for neural networks. Sounds really familiar to what TensorFlow is, so what's the difference here? Well, Keras is a more user-friendly library, and you'll see how user-friendly it is when we get into these actual modeling, because it's built in a very sequential type way, where you have some model architecture in mind, you know the steps you need to do, and the way you code this model in Keras is basically just building blocks wise. This is the first step, I'm going to add this step next, this step comes last, and it's quite easy to interpret and understand. So it's a user-friendly library. How does it relate to TensorFlow? Well, TensorFlow can be used as its backend, or another way to say that is Keras is built on top of TensorFlow. It's talking to TensorFlow, it's just that it's a lot easier for us to interact with Keras rather than TensorFlow directly, and that's why people often use it. So that's enough about that. All the other imports are pretty standard. So let's get started with our first, and you might think very, very silly sequence modeling task. Our first sequence is going to be just the integers from 0 through 9. We're going to feed our model 3 of these integers in a sequence. So for example, I'm going to say, hey model, 0, 1, 2, what comes next? And it better give me 3. Or I'm going to give the model 5, 6, 7, what comes next? And it better be 8. Seems super silly, but it's quite instructive and quite interpretable, as we'll see, to start with a very basic problem like this. So I won't go through exactly what's happening in all these NumPy operations, but I'll output as much as possible for you all so you can keep track of what's going on. With any machine learning model, we're going to generate training and validation data. Our training data here looks like this. This is the first 3 examples in our training data. The first example is the sequence 0, 1, 2. Let's take a look at the label corresponding to that training example. The label is 3. All that's saying we're giving the model 0, 1, 2, and we're saying the next thing would be 3. Similar with these other training examples, give the model 1, 2, 3, you tell it the next thing is 4, give the model 2, 3, 4, you tell it the next thing is 5. So it has a bunch of examples like this. Now we can go ahead and just get into training the model. And here's where the beauty and simplicity of using Keras to build your model really shines. So the first thing is we initialize the model. We say that model is equal to sequential. And now we just do an add call. In this case, we're just doing a single add call, but as we'll see a little bit later on, you can add basically as many steps as you want, each one coming after the next one. So the first thing we're going to add to our model is an RNN layer. This first number here is the number of dimensions in the hidden state. So we're keeping things super simple here because this is a pretty simple problem. And we're saying there's only one dimension in the hidden state. It's a vector of size 1. In other words, it's just a scalar. And you also get to specify the activation function. Again, this is such a simple problem, we don't need any fancy sigmoid or tanh activations. In fact, a linear activation is perfect here because the sequence we're learning is linear. Each item in the sequence is just +1 from the previous thing in the sequence. So linear is the perfect thing to use here. We go ahead and say model.compile. So we specify here what's the loss function we're going to be using. We'll choose mean squared error here. We go ahead and specify the optimizer we're going to use, which is defined in the line just above. And we also specify the metrics that I want to track as the model goes about its training. So in this case, the metric I'm tracking, mean squared error, is the same as my loss function, but it doesn't have to be. And then that's it. We go ahead and just call model.fit, pass in our training data, pass in our training labels. We pass in the number of epochs. Epochs is a fancy word for just how many iterations do you want the model to train for. And there's a whole science that goes into this. We won't get too much into that here. But you'll see as the epochs go on, our mean squared error on this training set is decreasing and decreasing and decreasing. So we know that it's doing better and better and better on the training set. Of course, you also, as always, need to think about how it's going to do on the validation set. And we're going to set verbose equals 1 so that we can just keep track of what's going on. And so let me walk you through a training of one of these models and how to read all this. And the main two things we're going to care about are the loss function and also the metrics we care about. In this case, they're the same, so just look at whichever one you want. They're both mean squared error. We see that after one epoch, the mean squared error is quite high. It's 15.7. And again, these numbers are between 0 and 9, so for the mean squared error to be 15.7, that's quite high. But worry not. As we train more and more and more epochs, and so these epochs are related to the topic of back propagation, which we also have a video for, which I'll link below. Each epoch is the model's attempt to learn more and more and more and more. So we see that as the epochs go on, surely, slowly but surely, this mean squared error is dropping. We reach below 1. Good news. We keep going, we keep going, we keep going, we keep going. Now we're getting to this really small number territory. It's basically doing perfect performance on this training set. And by the time we get to 100 epochs, you can see we didn't even need 100. We could have stopped much, much earlier. We've reached a mean squared error on the training set that is practically 0. It's received perfect performance on the training set. Now that should give you some alarm bells, like how is it doing on the validation set, but we'll get to that in just a moment. The other very nice thing about Keras, you can do model.summary, and it gives you a breakdown of what steps are happening in your model. Again, here it's not too enlightening, but if there's one number here which helps us shed light on exactly how this RNN layer is working and how it's different from the RNN we learned in our theoretical video. So here we see there's just one layer, the simple RNN. You can see the shape of this layer. So this is basically saying it's going to output that single scalar because we said there's only one dimension in this hidden layer. And we see there's 3 parameters. Now, pause here for a second. I was confused. Why are there 3 parameters? If you go back to our RNN theory video, there should have been 4 parameters. There should have been 1 weight on the new inputs that were coming in, these x's if you go back to that video. There should have been 1 weight on the previous hidden state, so that gets us to 2 parameters total. There should have been 1 parameter for the bias term, and there should be a 4th parameter for the translation from the hidden state to the output state. So I was confused. Why is it 3 and not 4? What are we missing here? So I found eventually this Stack Exchange answer, which says that the simple RNN in Keras is simply using the output layer as the hidden state. They are one and the same here. So this is a little bit different from the theoretical video we had, where we had a hidden state and an output layer. Here they are one and the same. So this is actually simpler to even think about. But if you were confused, as I was, that's the reason. Getting back to it, now we have a model now. We've trained a model. It has proven to do really, really, really well on the training set. And so let's predict using the model. So let's first predict on all of the training data. We know it's already going to do well, but we can learn a little bit by looking at the predictions themselves. So we're going to print some outputs here. We see that if we give the model 0, 1, 2, its prediction is 2.9999, so essentially 3. Great. If we give it 1, 2, 3, its prediction is 4. If we give it 2, 3, 4, its prediction is 5. So on known data, it's doing great. We can plot a chart here, so we can look at predicted versus actual, and we see it's perfect. All these red points line up with this dashed line, and we know the model is doing great on the training data. But more interestingly, how would this model generalize? So just to remind you, we trained this model on the integers between 0 and 9. it's never seen anything in the training data that is beyond that range. And so if I test its knowledge, I give it 6, 7, 8, which it has seen. I give it 7, 8, 9, which it has seen. But now I get into territory it hasn't seen, 8, 9, 10, 9, 10, 11, 10, 11, 12. Will it be able to learn what comes next? Or is it only good on the training data it has seen? Turns out it has learned properly what's going to come next. So we see down here, if I give it 9, 10, 11, even though it's never seen the numbers 10 or 11 before, it knows that 12 should come next. If I give it 10, 11, 12, even though it's never seen the numbers 10, 11, or 12 before, it knows that 13 should come next. So it's good news. It's doing what we would expect it to do. Now, since we have such a simple example here, it would be a really good opportunity to take a look at why does this work? Neural networks are known for being really powerful, but interpretability is always a little bit more of a struggle with neural networks than with more interpretable models like trees or linear regression, logistic regression, all those sorts of things. But since we're in such a simple world here, we can actually understand exactly what's going on. There's only 3 weights at the end of the day. And here are those 3 weights. And I've also written the letter corresponding to the weights, that letter being the letter you would see if you watch the theoretical recurrent neural networks video. So the first weight, U, is 0.93. The next weight, V, is going to be 0.07. And the last weight, B, the bias, is going to be basically 1.0. So the model has learned that Y sub t, so the output state or the hidden state, remember in this case they're the same, and there's no activation function here, so there's no sigmoid or tanh or anything. So it's learned that the output state is 0.93 times the input state, plus 0.07 times the previous output state or the previous hidden state, plus the bias term of 1. Now we can simplify this because what is y sub t minus 1? Y sub t minus 1 is the previous output state. And the previous output state should be what comes after the previous input state. In other words, if I pass in xt minus 1, then yt minus 1 should be the next term after xt minus 1. Then that means that yt minus 1 is exactly x sub t, which is what would come next after x sub t minus 1. So I know that was a lot of subscript talking, but go ahead and pause if you want to convince that for yourself. But either way, we can simplify to the second line, and now we have x sub t here, add these together, and you get that the model has learned exactly the rule of the sequence, which is y sub t, aka the next state, should be x sub t, aka this state, plus 1. Take the current number, add 1, that's your next number. That's exactly what the model has learned, which is awesome. Now, as much as I'm talking up this model, let's not forget that this was such a simple problem. You can solve this with a linear regression. I won't go too much into all this code, but you can see that the output of training a simple linear regression, arguably the most simple model in all of data science, the first thing you learn in your statistics course, it learns the exact same thing. The linear model learns that after 6, 7, and 8 should come 9, after 10, 11, 12 comes 13, nothing special going on. So an RNN was definitely overkill for this problem, but it did help us understand a lot about what's going on under the hood, the architecture of the model, building and training a simple model in Keras. So let's take it one step further and come up with a data sequence that a linear model would not be able to solve. So that sequence will be this one. This is a sinusoidal sequence with a little bit of noise added to it, and you can pretty easily see that a linear model won't be too effective here. In fact, if we try a linear model on this data, the predictions are here in orange, it pretty much just breaks down. So let's go ahead and train an RNN here. Let me point out just the different things here. So I'm adding a RNN layer, and now it's going to have 2 units in the hidden layer. In other words, these vectors that are in the hidden state or the output state are going to be size 2. It's going to be some number and another number instead of just a single one. What does it do when you increase this number from 1 to 2 to 4 to 8? Well, you give the model more flexibility. Now you're saying for any given input, I'm actually giving you 2 different ways to represent that input, 2 different functions you can apply as features for that input. So in a nutshell, it gives the model more flexibility. We're also going to change the activation function to tanh, because this is no longer a linear problem, so it might help to give us some non-linearities. But you'll notice now, the output of this RNN is going to have two numbers in it. But at the end of the day, we just want to predict one number. And so we add another layer. So this showcases the kind of building block nature of Keras. I added a simple RNN layer, and then I add a dense layer. A dense layer is a vanilla neural network. In other words, just a basic neural network, not recurrent, nothing special going on. We're basically just building a neural network that's going to take in this vector of size 2 and turn it into a vector of size 1. Everything else has remained the same. We trained this for just 25 epochs. We see it receives pretty good mean squared error on the training set. And if we look at now the predictions from this recurrent neural network, it has captured very closely the behavior of this sine wave. It's learned that what should happen after this is I should go up and up and up and up, but after a certain point, I know that I should plateau. I shouldn't just keep going. I shouldn't sharply go down. I shouldn't sharply go up. It's learned the sequence of the sine wave. And so while this does showcase the power of the RNN a little bit further, it's still not super impressive. You could have captured this with quite a much simpler model. You could just use a sine function, for example. But hopefully you see now that RNNs are doing a good job at sequence modeling. And now to close this video out, I want to show you an application of recurrent neural networks to something where none of these previous approaches, linear regression or decision trees or support vector machines, are readily applicable, and which is an application of natural language processing. We are going to be using a data set of movie reviews. So you go watch a movie, you go watch Thor: Love and Thunder, and you say, "It sucks. I hated that movie." We want to use that text of someone's review in order to predict whether their review was positive or negative. Now, the application of this is very straightforward, and you can think of so many other applications of taking text and translating into positive or negative sentiment as well. This is a whole field, a whole study in NLP called sentiment analysis. Given some speech someone says, can you tell if that speech was positive intent or negative intent? So let's go ahead and see how we're going to do it. You can follow along too. A lot of these beginning cells were taken from this tutorial TensorFlow notebook. And so the beginning stuff is not too enlightening. We're simply just downloading the data. We are doing a little bit of data cleanup. The first interesting cell is here. So you can see we've printed out 5 examples in this data set. The first number you see here is 0 if it is a negative sentiment movie review, and it's a 1 if it's a positive sentiment movie review. So let's take a moment and read through one of these to see just how subtle they can be. Let's look at the negative one. "Oh my God, please, for the love of all that is holy, do not watch this movie. It is 82 minutes of my life I will never get back." So you can see that people, obviously, especially with reviews, where they want to express their love or hate of a movie or a product or a restaurant, are using really powerful and often complex language. And that really begs us to use these sequence modeling problems because you want to see what word leads to what other word, leads to what other word, leads to what other word. It's going to be really powerful for us to read this as a person would read this and use that to make a judgment about whether this is a positive or negative review. So that was a negative one for sure. Here's a positive one. "This movie is so funny. The acting is wonderful. The Ramones are sexy. The jokes are subtle," and so on and so on. So this is obviously a positive review. So we have several such examples, and we're hoping to predict the label here. Now, there is a little bit of pre-processing that goes into text data. Before, when we're working with numbers, numbers are just ready to feed into our neural network. With text data, we need to do 2 steps, 2 high-level steps, before we're ready to feed this as numbers into our neural network. The first thing that needs to happen is each of these words. So if I scroll up here, there's many words, right? Movie, actual, theater, so many different words. Each of them needs to get mapped to a unique index that corresponds to that word. And that is exactly what this vectorized layer is for. So this vectorized layer is basically just saying for each of these unique words, map it to an index. Now we are not looking at the word movie anymore. We're looking at a number, for example, 0. Now the next thing that needs to happen is we need to have a rich representation of each of these words. So for example, movie needs to get represented as a vector, or in the terminology, an embedding of some kind. So we're going to be learning alongside the RNN, we're actually going to be learning 5-dimensional vectors or embeddings for each of these words. Now this is quite a common technique in natural language processing and recurrent neural networks and all the things built on top of recurrent neural networks, which is when you're using it for natural language processing, you'll have words. You'll learn the embeddings or representations of these words that are best suited to solve the specific problem at hand. So for example, right now I'm trying to take a movie review and predict the sentiment of it. Another task I might want to do with this movie review is, for example, predict if it was said by a critic or an audience member. Now, the embeddings I learned for this task and the embeddings I learned for the critic versus audience member task may be completely different. So the model is learning the embeddings best suited for us to solve the problem at hand. And so you can see here where we're constructing the model. We have that vectorized layer, which is going to translate our words to indices. We have our embedding layer, and we're telling the embedding layer, so I apologize here, it wasn't a 5-dimensional embedding, it's actually much richer. We're using a 16-dimensional embedding here. We're telling the embedding layer, hey, I want a 16-dimensional embedding learned for each of my words. And then we have the simple RNN layer, just like we did before. We're giving it 8 hidden units here. So 8 is the size of the hidden layer, the output layer. And then we have a dense layer, again, just a typical vanilla neural network, which is going to take the 8-dimensional vector coming out of the simple RNN and map that to a single number, the probability that this is a positive movie review. So we go ahead and fit the model. The new things we're adding here is a validation set, so we can track, while the model is training, the performance also on the validation data set, which is going to be crucial. So the validation accuracy after 1 epoch is just 60%. That's already pretty good. Then we have 71%, 73%, it's going up, it's going up, it's going up, it's going up, and we end around 75%. But interestingly, that's not the highest one we saw. We actually were able to get it in the 77% range. It's possible that as it continued learning, it was actually overfitting. So you can see the loss on the training data is going down, but it's not getting better, it's actually getting worse on the validation data. So this number of epochs is something that's worth keeping an eye on and tuning. So this model.summary is a lot more enlightening to look at. It actually gives a full picture of exactly what is happening here. So this summary is telling us that the first thing that happens is the text vectorization layer, which again is responsible for taking these English words, these strings, and mapping them to unique indices. We've chosen to use 100 words per review. And so for that reason, the size, the output size of this is 100, each one corresponding to a word in the movie review. Next comes the embedding layer. The output size of this is 100 by 16, because for each word in the movie review, we're learning a 16-dimensional vector. So it's a matrix you can think of, 100 words, 16 columns or 16 dimensions in the embedding of each word. Then what comes next is the simple RNN. We're saying that it is outputting, or the hidden state is 8 dimensions big. And finally, we have the dense layer, which is just returning a single-dimensional number, a scalar, which is the probability that this review is positive. So there's a ton more parameters than there were before. There's like on the order of 160,000 here, definitely bigger than 3. And so we see that there is a lot of moving parts in this model compared to the previous ones that we learned. Now, that's it. This is the last cell. We are ready to start just putting in potential sequences into here, just reviews that we can think of, and seeing what the model thinks about them. I think this is a really cool thing about RNNs and everything that we're going to learn based on them, which is you can just type free text and it's going to run that through the model, do all of these steps that we see in this summary here, and output a probability that someone likes this movie review, or the probability that this is written by a critic, or anything you can think of, any output label you can think of. So let's just start playing with it. We can start simple. We can start with something nobody would ever write, this explicit, but I love this movie. So you can see the output here is 0.908, very high probability that this is a positive review. Let's check the other side. I hate this movie. Very low probability, not as low as I would have expected in quite honesty, but it's less than 50%. You can say, I think this movie was a waste of money. Very low, that's good. That's definitely not a positive intent, that's negative intent. The acting was really good. Ooh, so that's not a good case here. So this is kind of showing us where the model is doing well and where it's not doing well. What about something that's kind of a mixed review? Not all reviews are positive or negative. There's sometimes people put in things that are kind of in between. So you can say, I thought the special effects were good, but the plot was pretty bad. So this should give us something around 0.5. Wow, that's great. Gives us pretty much right down the middle. Not positive, not negative, something in between. So I wonder how this works if we put in real movie reviews. So let's say Thor, Love and Thunder reviews. So let's just copy paste something someone actually typed in and see how this simple RNN we learned is dealing with it. So let's go ahead and copy this fine person's review. Just copy the entire thing here and just paste that whole thing in there. 0.58, and if we read this, do we agree with that? 10 out of 10, this movie has to be in my top 10 greatest movies of all time. They gave it 5 stars. And you can definitely play around with this, put in your own reviews and see if the results make sense to you or not. Change the model architecture, make it less complex, make it more complex. Now that you have a basic understanding of how to add things in Keras, how to add new components to your model in a very modular fashion, the world is your oyster. You can use this for any real sequence modeling task that you can think of, natural language or time series or otherwise. So if you learned something in this video, please leave a like and subscribe to this channel for more content just like this. Any questions are always welcome in the comments below, and I will see you fine people next time.